So welcome again, everybody. I have been looking forward to this class as always. The weekend was quite long. So let's get started. If you have any questions in the course of the lectures, please feel free to ask. And make sure I get your questions, even if it means that you have to cry before I get it. Now, make sure it's important you ask your questions. So let's get started. Work. We know that this is just a review of what we've done. Work is the energy transferred when a force does what? Moves an object from one position to another in the same direction as the force. Let me put it this way. Work is energy transferred when a force moves its point of application. Now, by definition, W is going to be equal to what? The integral of F dr from R initial to R final. Now, we showed that from Newton's second law that F is equal to what? M dV dt, which is the same as mv dV dr. This would imply that W is equal to the integral of what? mv dV dr dot dr. This takes care of that. This becomes mv dV. And if we integrate, we will have half mv squared from V initial to V final, which gives us W to be equal to what? Half m V final squared minus half m V initial squared. We actually derived this last class, and we said that this is known as the work kinetic energy theorem. This is known as the work kinetic energy theorem. Now, it may look very simple, but it has very important consequences. Now, the very first thing that you need to note about this. Now, a system is anything that our attention is focused on. It could be a book, it could be a set of books, it could be a single object, it could be what a group of what objects interact with each other. Now, when a system consists of more than one object, the objects can interact with themselves as well as with the surroundings. Do you understand? Please pay attention to the class, not to the pics. Look up, please. Look up. Look up. When the objects within a system interact with themselves, they generate what we call internal forces. But when an object interacts with the surroundings, they generate what we call external forces. We know that one of the consequences of Newton's third law of motion is that the net internal force in a system is always what? Zero. This implies that the motion of a system, in other words, the kinetic energy of a system can only change only when external forces act on the system. Do you understand me? Listen carefully to the next sentence I'm going to give. I'm going to repeat what I've said, but pay attention to the next sentence. The kinetic energy of a system can only change only if, or if and only if, there is a net external force acting on the system. This means that work can only be done. This means that the net work done on a system is due to what? A net external force acting on a system. So the important statement is this. The work kinetic energy theorem implies that only external forces can cause a system to do what? Move, which is in phase with what we concluded from Newton's laws of what? Motion. Do you understand me? Which is in phase from what we concluded from Newton's laws of motion. Now, the next thing I would like for us to talk about is the rate at which work is done. Rate of doing work. Rate of doing work, which is simply called power, pouvoir en français. Now, power is a word that is commonly used in our daily language, which has a different connotation or meaning from how we use it in physics. So you need to be very careful here, especially when it comes to multiple choice questions. Power basically is the rate at which work is done. Listen carefully, please. Listen carefully. Power is the rate at which work is done. This may not make sense. Whenever work is done, energy is what? Transferred. This means that power is the rate at which energy is what? Transferred. It is possible for two objects to do the same amount of work but have different what? Powers. For example, if David, please stand. Akash, stand. Both of you, go stand behind the class. Let's do a simple experiment. Now, David, walk very fast to where you were sitting. Akash, walk slowly to where he is standing now. Good. Observe something. At the end of the journey, both have done the same amount of work, but the rate at which David did work is so different from the rate at which Akash did work. You understand that, right? So one has more power than the other. According to WWE, the guy who has more power is the guy who can punch the more. And it doesn't work like that in physics. You understand that, right? It doesn't work like that in physics. All right, thank you, please. Great demonstration. Sit down. Now, look up, fellas. Look up. Look up. Power is dW over dt, the rate at which work is done. This means that this is d of Fr dt, which is going to be F dr over dt. Now, Sanjali, what is dr over dt?
dr over dt.
R is position. What is dr over dt? Velocity. So this is equal to Fv. So power, or the rate of doing work, is force times what? Velocity. It is also important for you to understand that that power is the rate at which energy is what? Transferred. This definition, don't forget, is equal to the rate at which energy is transferred. Power is a scalar quantity measured in watts, capital W. So 1 watt is equal to what? 1 Newton multiplied by what? Meters per second, which is the same as 1 kilograms meters per second squared multiplied by meters per second, which is equal to 1 kilograms meters squared per second watt cube. That is the equivalent of 1 watt. This makes the watt what kind of a unit? Derived or basic? Derived. All right. Pick up your clickers. Look, watch everybody. This object is initially at rest. which means at t equal to 0, v is 0. Then F acts on this object and accelerates it to a particular velocity v. The question is, what is the average power delivered by this force F? The answer A is F 2m multiplied by t. The answer B is F m multiplied by t. C, F squared over 2m multiplied by t. D, F squared over m multiplied by t. Please vote in. Get to work. Jacob?
What is the question?
Can you give to right hand? Give to him behind the class, please.
Wait, no, you don't need that. Because you get the final velocity. So
Mr. J, I'm a little-
Yes, please.
I don't know what the question is.
Now, let me repeat the question again. Let me repeat the question again, please. The question says, a force F accelerates an object from rest to a particular velocity v. You need to calculate the average power delivered by the force. Calculate the average power delivered by the force. Feel free to discuss amongst yourselves, please. Pardon? Yeah, that could work. That's the way I did it.
Like, in order to find the power,
Yeah, you have to calculate the work and then divide by the time.
yeah, because power is the derivative of work.
yeah, that makes sense.
Yeah.
The rate of
Which means work is the integral of p dt, right?
So then it would be d.
I'm not so sure. Please voting. You have clickers. All right, log in, please. Your time is up. Log in. Log in. Your time is up.
Only half. One half of the cost.
Stephanie, everything okay? Okay, good.
Average, yeah. It's average. You need to rewrite it. Average power.
Wait, so wait, is this
All right, everybody, your time is up. Your time is up. I'm closing down the vote, please. If you have not logged in, log in now. Thank you. 100% of the class chose C. Yes, the answer is C. Okay, look up everybody. I know everybody got this right, but just to make sure, we know that, please look up, P is dW over dt, which means that delta W is the integral of P dt, which is going to be the integral of what? FV dt, which basically will be the integral of what? M, or we can choose to work. Remember, we want to calculate the average power, and P average is just going to be delta W all divided by delta T. This is the average power, right? which technically will be W divided by T, because initially W is 0. So how do we function here? Now, the object starts from rest. We know that V is equal to V naught plus 80, so this is 0. So V is equal to 80. What is A? From Newton's second law, it's equal to what? F over M, all multiplied by T. So if we put that in there, we will have F squared over M multiplied by T dt, which is going to be F squared over 2M T squared. If you then divide that by T, you will have F squared T squared 2M all divided by T. You will have here F squared over 2MT. And great, everybody got it correctly. Let's move on, please. Let's move on. Another unit, look up. Another common unit that you will see in the exam or in the AP is horsepower. Power is also measured in horsepower, and 1 horsepower is equivalent to 746 watts. This conversion will not be given to you in the formula booklet, but you're expected to know that. You are expected to know that. Please, question number 2. Question number 2. Let's not waste time on this. Be quick. The surface is rough.
Why can't they all be smooth?
Calculate the power delivered by this force. Calculate the power delivered by that force. A is mgv. B is mu mgv. C is mu mgv squared. And D would be mgv divided by mu. Calculate the power delivered by that force. Understand that the system moves with a constant speed.
Oh, okay.
Wait, with the what?
Constant speed.
The system moves with a constant speed. You know what that means?
No, that means F equals mu and G. This is constant speed.
It's constant speed, it's all the same level.
Yeah.
Are you gonna start?
Okay, so that's acceleration.
Please, I'll close the vote now.
Wait, what?
This is a trivial question. Look at it. It's constant speed. What does that mean? F should be equal to mu mg, right? And what is power? Fv.
Oh, so
Oh, it gives you in terms of V. Oh, okay, got you.
That makes up for the correction.
I was trying to solve for V.
Now, listen, please. Listen. Everybody has voted. Great. Now, the answer is B. When you hear the word constant speed in a straight line, it means that all the forces acting on the system are what? Balanced. In other words, F will be equal to the friction force on the object, which is going to be what? Mu mg, which implies that P, which is Fv, will be mu mgv. And the answer is B. All right, great, great. Any questions? Any question? The third point which we need to review is potential energy. We know that, listen, there are two kinds of forces acting on a system. Please, Pay attention for the next 5 minutes. Pay attention, because what we are going to discuss in the next 5 minutes by research is conceptually challenging, but yet simple if you just listen and try to get what I'm about to say. When a system consists of 2 or more objects, there are 2 sets of forces, internal forces and external forces. Internal forces are due to interaction of the objects within the system, and external forces are due to interaction between the objects in the system and the objects in the surroundings. Work is equal to force times the displacement of that force. So there are 2 kinds of work. You have internal work due to internal forces, and you have external work due to external forces. What is the difference between internal work and external work? Only external work can lead to a change in kinetic energy. Do you understand that? Now, following up with what we did last class, the internal work done in a system is equal to the potential energy in that system. Okay, you got in here in the morning pretty happy and full. By lunch, you are really hungry, just want to get out of this class and get a burger. Why? Because throughout the day, you have been doing work. And now when a system, listen carefully now, when a system does work, it does work at the expense of the energy of the system. So the total energy does decreases. The next statement, potential energy is the energy associated to internal forces. Let me say that again. Potential energy is the energy associated to internal forces. In other words, potential energy is the work done by internal forces to change the configuration of the system. Cool fact, whenever internal forces does work, the total energy of the system decreases. And when the total energy of the system decreases, will the work done be positive or negative?
Positive.
Will it be positive or negative?
Was it work done on the system or by the system?
By the system.
Then it's
Whenever, okay, listen this way. Thank you, Jacob, for that comment. Let me put this statement this way. When internal forces does work, is that work done on or by the system? By the system. And when the system does work, is that work positive or negative? Negative. This explains why dW is equal to negative FdR. The difference is that these forces are internal forces, and this defines the change in potential energy of a system. The negative sign is not to indicate that potential energy is a vector, no. It's just there to imply that the total energy of the system decreases. In other words, the negative sign is there because the potential energy is stored energy and is released or used up whenever internal forces does work. Do you understand me? Whenever internal forces does work. Now, I'm going to say this, and I'm going to say this just once. When doing problems in physics, to simplify your calculations, it is often very important for you to choose a reference point. And a reference point is a point where the potential energy is 0. So if we choose our reference point, our initial, to be 0, this means that UR will be equal to the integral of F dr from our initial to our final. This equation is very important. I know all of you here have done calculus, so I'm going to assume that you can interpret it. So who can interpret this from your calculus perspective? Okay. Can we solve this equation if f is not a function of r? If f is not a function of r, is this equation solvable? Okay, let me make it concrete. If I say that the integral of 3t squared dr from 0 to 4, can we solve this equation?
Yes. No.
You need other stuff.
We cannot, because because this function has to be a function of what? R. Do you understand me? For example, if we have 4r squared dr, this is quickly solvable because it's going to be what? 4 over 3 r cubed plus a constant, isn't it? So this function has to be a function of what? R, for this equation to be solvable. R stands for what? Position. Listen carefully. R stands for position. The path, listen, I'm going to use a word that is common but frequently used. The path of a particle is known if R is known for all values of what? T. Listen now. So the implication of this equation is this equation can only make sense only if f is a function of what? Position. Let me say that again. That equation can only make sense only if f is a function of what? Position. Secondly, this is the first. The second is potential energy is a path integral. Potential energy is a path integral of what? The force acting on a system or within a system.
What does that mean?
That would mean that the potential energy function can only be defined if and only if the force is a function of what? Position. Write that in red.
Think about force again.
Let me say that again. Let me say that again, please. The potential energy of a system, the potential energy of a system or the potential energy function can only be defined when the force is a function of position only. Underline the word only. This has a big implication. This has a big implication. Look up now. Look up now. The first implication will lead to a very important definition. If we have Jeremy, you're all smiley. I hope that you're enjoying the lectures. Now, look up, everybody. Look up, please. Look up. My fellow students, if you understand this, it will help you. If you understand these two units, you're guaranteed a 5 in AP Mechanics. And that's why I'm spending quite a bit of time explaining this. Okay, look up, fellas. Look up now. Pens down. Pens down. This is the potential energy function. We know that by definition, watch, work is defined as the integral of f dr from r initial to r final. This is, suppose an object moves through path A from 1 to 2, then the work done from part 1 to part 2, which is equal to WA, will be the integral from 1 to 2 f dot dr. Yes, please?
Why is the 1 drawn on the...
You mean where? Here?
Like, why is it drawn on the potential energy line?
This is from point 1 to point 2.
Oh, okay. That's it.
You understand, right? From point 1 to point 2. If you have any question, ask. Please, it's important you ask. I need you to understand this. Look up, everybody, please.
Wait, what is 1, 2 again?
Point 1 to point 2. This will be R1 to R2. Similarly, look up, fellas. Similarly, W from point 2 to point 1, which is WB, will be the integral from 2 to 1 f dr. Observe me now. I'm going to do something trivial but with good consequences. If we integrate the limit, what do we do here?
That'll be negative.
We insert a negative sign. This is f dr.
Wait, what did the other one be?
Pardon?
Oh, never mind.
This is equal to, Brian, the bigger one. Now, the question is this, please. What is this? It's equal to WB, right? Do you agree with me? So this is negative WB. This would mean that if we take this to the other side, WA plus WB will be equal to what? 0. So if an object moves from point 1 to point 2, and then from point 2 to point 1, the total work done is 0. This can only be true if and only if f is a function of what? R. When a force obeys this condition, it is known as a conservative force. When a force obeys this condition, it is known as a conservative force. Angeli, do you have a question? Okay, good. Good. David, any questions? Steph? Do you have a question? Now look up, everybody. Look up, please. Look up. Write this statement down. Write this statement down. A conservative force is a force that does no work around a closed path. Is a force that does no work around a closed path. Let me demonstrate to you some examples of conservative forces. Now, what is the unique characteristic of a conservative force? It is a function of position only. It is a function of position only. Let's do this. Yes, please.
Does conserve force imply conserve?
There is nothing. Thank you for asking that question. Reason being that there are some multiple choice that talks about conservative forces and a conserved force. In science, in general, there is nothing like a conserved force. But there is...
Oh, I mean conservative forces?
Yes, conservative forces.
Okay.
Okay, look up everybody. Look up, please.
No, but can't you say like the energy is conserved? Or like...
Energy can be conserved, but forces cannot be conserved.
So in conservative forces, is the
A conservative force is a force that does no work when it moves around a closed path. Let me show you an example. Then you can ask your question after this example, all right?
Yeah.
Yes, please. Wait until I finish this example. Now look up everybody. Look up please. We have this distance here is x, this height here is h. You have Peter, he climbs upstairs and climbs down the stairs and walks back to this position. So this is A, this is B, and this is C. Let's calculate the work done by gravity. So WAB, remember gravity is acting vertically downwards. His climbing upstairs is going to be equal to what? Generally the definition is F delta R cosine theta. So WAB will be equal to mg H cosine of 180 degrees, which is going to be negative mg H. WBC is going to be what? Mg H cosine of 0, which is just going to be mg H. Then WCA is going to be mg multiplied by what? This distance AC cosine of what? 90 degrees, which is going to be what? 0. So the total work done, W by gravity, is going to be negative mgh plus mgh plus 0, which is equal to what? 0. So the work done by gravity around this closed path is what? 0. So gravity is an example of a conservative force. Gravity, or the gravitational force, is an example of what? A conservative force. Do you understand that, right? Now, Akech, you're free to go, but be fast. I'm not going to wait on you. Look up everybody. Look up everybody. I need for you to write this statement in red. You already know this, but I'd like for you to put it down, everybody. In your notebooks. 1. Whenever a conservative force does work, the potential energy of the system increases. True or false? True or false?
You repeat it.
Whenever a conservative force does work, the potential energy of a system increases. True or false?
False.
False. It decreases. That was statement 1. Statement 2. This is the third time you're writing the statement, and write the statement again. Potential energy is only associated to internal what? Forces. Put a double star on the third statement. Associated to every associated to every conservative force, you're writing, associated to every conservative force is a potential energy function. Associated to every conservative force is a potential energy function. Okay, let me clarify. When I use the word potential energy function, it is just the potential energy at a particular position. It's just a fancy word for potential energy at a particular what position. Now look up, everybody. Let me show you what I mean. Let me show you what I mean, please. Heads up. We know that delta W is equal to negative the integral from R initial to RF F dr. Basically, this would mean that F of R is equal to negative du over dr. This equation is very important. Which means that F of X is equal to negative du dx. F of Y is equal to negative du dy, and F of Z is negative du dz.
That should be dz, right?
Yeah, dz, thank you. Understand that U is the potential energy at a particular what position, known as the potential energy function. Let me give you an example. Suppose that U, X, Y, Z is equal to X squared plus XY plus YZ. Determine F of R. Determine F of R. Look up, let me show you how this is done. Every year in the AP, you will see something like this in the multiple choice. And these are easy points to get. So we have F of X is negative du dx, which is going to be negative d of dx of x squared plus xy plus yz. When you are integrating a function like this with respect to x, you will assume that y and z are what? Constants. So this is going to be negative 2x plus y plus 0. Therefore, f of x is equal to negative, there is a negative somewhere here. So this is negative 2x plus y newtons. Similarly, f of y will be equal to negative bracket, this is 0, this will be x plus z, and f of z will be equal to negative, this is 0, and this will be what? Y. Hence, we can see that f of r, look up now fellas, will be equal to negative bracket 2x plus yi plus x plus zj plus yk. So this will give us the expression for the force acting on the particle. To make sure that you've understood, everybody should do this problem. Given that u is equal to 5xy squared, this is actually taken from your textbook, 3xyz plus 10x cubed z. Determine the resultant force acting on a particle with such a potential function. Everybody get to work. Get to work. You can use your whiteboards as well as the walls, everybody.
Rod, did you already get it?
What? A little racing the
Why
previous
is
answer.
everyone saying good job?
I have no idea.
Ralph and Genie.
When is our next class?
Good question.
Next week.
Next week.
Day.
I mean, I actually don't know. Monday, right?
I'm going to post your take-home test on Moodle,
That's
Wait.
but it will be due 2 days after we come back from break.
two classes or 2 days?
Pardon?
2 classes or 2 days?
2 classes.
What is that?
No.
So Wednesday.
On Wednesday. You get back on Monday. The class will be on...
Monday and
and Wednesday. So it's due on Wednesday.
Yeah, on Wednesday, yeah.
Okay.
And you have X,
Plus
Y.
3 minus, yeah, plus 30x squared.
I don't get it.
Oh, X, 10, X.
David, are you done?
Could someone do the middle one for me?
Ralph, don't be lazy.
Isn't this just partial derivatives?
That's partial derivatives, exactly. That's just partial derivatives. Good job.
Yeah.
Did you even see that? Where were we? Like, where were we? I think it was the like sitting.
Multi?
We haven't done that.
That was the.
Real lit?
Yeah.
Well then.
That's right.
Like this.
Remember, please, listen. Listen, this is just ordinary differentiation if you keep in mind when you are integrating u with respect to x, y and z are constants.
Oh.
When you're integrating u with respect to y, x and z are what? Constants. And when you're integrating u with respect to z, x and y are considered to be what? Constants. Keep that in mind.
Okay, that means like.
Yeah. Can I get it? Multi coming the
Yeah, okay, so it's not,
You should be done by now.
yeah.
Are you satisfied?
Okay, look, this one, y is a constant. So it's so 5y squared.
Because I don't know.
X, right? So it's 5y squared. Plus 4yz, and differentiate this. C is constant. So when you differentiate y, x, and z constants, then for z, x, and y are
What are you guys doing? Are you guys seeing this?
All right, look up, everybody. Look up, look up. Yeah, most of you are getting it right. Look up, please. Look up, look up. Look up, everybody, please. Thank you. Everybody have checked, got it correctly. For those of you struggling, let me do this one more. Let me do this one more. So if you have any questions, ask in the process. We know that, look up, F resultant is equal to Fxi plus Fyj plus Fzk. This is the same as negative du dxi negative du dyj negative du dzk. We know that du dx is equal to, we will keep y and z as constants. So we will have here 5y squared plus 3yz plus 30x squared z. Du dy will be equal to 10xy plus 3zx plus 0. Du dz will be equal to 0 plus 3xy plus 10x cubed. So if you substitute this in there, you should be able to get what? Your fx. Is that okay? Look up now. Let's move on to the next point. Let's move on to the next point, please. Look at this equation. Please look at, yes please. Just wait after this point. This is pretty important. F R is equal to negative dur over dt. Sorry, dr. In terms of calculus, I need for you to be comfortable with the terminology that we are using now. In terms of calculus, F is the potential energy gradient, because this is a gradient. That is the definition of what? Differentiation, right? The slope, the gradient. Do you get me? So write that one, write that down, please. Write that down. Fr is equal to the potential energy gradient. So if you are reading a question and you read the phrase potential, determine the potential energy gradient, you are determining what? The force.
Is that F of R?
Yeah, that's F of R.
Not F times R, right?
No, F of R. Yeah. This is 1. 2. What does the negative sign implies? What does the negative sign means? Who can give me what it means? Yes?
That as the potential energy increases, the force decreases.
Great. As it means that as the potential energy increases, the force decreases. In other words, F, write down this statement, points in the direction of decreasing potential energy F points in the direction of decreasing potential energy. And the 3, F is equal to the slope of UR versus R graph. UR versus R graph. UR versus R graph. F is equal to negative the slope of UR versus R graph. Let's move on to the next, please. FR. What is the name of FR? Is it a conservative or non-conservative force? It's conservative. Conservative forces are forces which are what? Functions of position only. Now, conservative forces, listen carefully, I'm introducing another new terminology, can either be attractive or repulsive. Can either be attractive or repulsive. Now, attractive conservative forces are negative. Repulsive conservative forces are positive. I'll explain why. Let me say that again. Conservative forces can either be what? Attractive or repulsive. Attractive conservative forces are negative, and repulsive conservative forces are positive. How do you know if a conservative force is attractive and if a conservative force is what? Repulsive. An attractive conservative force is in the opposite direction. An attractive conservative force is always oppositely directed to change in R. In other words, an attractive conservative force is directed in the opposite direction to increasing R. Is directed in the opposite direction to increasing R. Now, a repulsive conservative force is directed in the same direction as what? Increasing R. That's why it's positive. That's why it's positive. Another way of knowing, this is the most common way portrayed by past AP questions. Look up, everybody. If du over dr is positive, this implies that fr will be what? Negative. In this case, fr is attractive. Fr is attractive. B, if du dr is less than 0, this implies, please look up, this implies that fr is greater than 0. In this case, fr is repulsive. And you know what that means? It means that, okay, let me interpret this conceptually to you. In case A, look up, fellas, look up, please, look up. In case A, is the speed of the object decreasing or increasing? Will the speed of the object be decreasing or increasing? Remember, F is directed in the opposite direction to what? To the force. Will the speed be increasing or decreasing? Sorry, F is directed in the opposite direction to increasing R.
Oh, that is the.
Then it's decreasing, right? Now, in case B, V will be what? Increasing. Do you see with me? Do you see with me? Do you have a question?
No. I'm just
Okay.
waiting.
You're processing it?
Yeah.
Okay.
I will.
Uh-huh. Yeah, you can. You can go now. Okay. The last but not the least, C, look up please, if du dr is 0, this means that fr is equal to what? 0. When f is 0, it means that what? The system is what? In equilibrium. It means that the system is in equilibrium. This is a consequence of which law of motion? The consequence of which law of motion? First, second, or third? The consequence of which law, please? First law of motion. In the absence of a net force, the system remains what? In equilibrium, right? And the most important fact I want you to note here is this. A system in equilibrium has what kind of a potential energy function? If du dr is 0, it means that what? U is a... What is the derivative of a constant? 0. It means that the potential energy function is a constant. So one quick way to know a system at equilibrium is to look at the potential energy function. If the potential energy function is a constant, then we can conclude that the system is in equilibrium. Do you understand me? Then we can conclude that the system is in equilibrium. Now, look at this graph. If we have a graph like this, this is A, this is B, C, D, and E. This is U, and this is R. Between A and B, is the slope positive or negative? Is the force positive or negative? It means that is the object accelerating or decelerating? Okay. Let's rewind. Let's go back here. Let's go back here. That's why I asked you to pay attention to this. Listen, 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 please. Listen. If you do not understand, please ask questions. You will see this in my exam, you will see this in the AP. You have no choice. Therefore, it's important you understand this. And if you understand this, electrostatic becomes easier for you. So please pay attention. A conservative force, which is a position-dependent force, can either be attractive or repulsive. Now, an attractive conservative force is always negative, and a repulsive conservative force is always positive. The negative sign is because the attractive conservative force is directed in a direction opposite to the direction of increasing what? R, increasing position. Which means that if the object is moving to the right, the force will be pointing to the what? Left. In that case, the object will be what? The speed will be decreasing. On the other hand, a repulsive conservative force is positive, meaning that it is directed in the same direction as increasing what? R. Which means if the object is going to the right, the force will be acting to the right, and therefore the what? The speed will be increasing. Do you understand me now? Let us interpret these sentences in terms of potential energy function. We know by definition that by definition F is negative du over what? dr. What does this mean? It means that if du dr is positive, then F is what? Negative. And if F is negative, it means it's what? Attractive. Do you understand the analogy? On the other hand, if du dr is negative, negative makes what? Positive. In that case, F will be positive, which makes it repulsive, and the speed of the object will be increasing. So let's go back to this graph again. When you are given a potential energy graph to interpret, look at the slope of the graph. Negative, the slope of the graph signifies what? The resultant force acting on the object. Between A and B, in the region AB, we know that du dr is less than 0, which implies that F is greater than what? 0. In this case, the force is, the object is accelerating. Great. At B, listen, at B, the object is in equilibrium because the slope at this point is 0. Between B and C, du dr is positive, which means that the force is what? Negative. So the object is what? Decelerating to what? To rest at C. Do you understand me? And the cycle repeats itself again. So here the force is repulsive. Here the force is what? Attractive. Any questions? Please, any questions? The next thing I would like us to do, let's look at the nature of equilibrium position. The nature of equilibrium positions. You may be wondering, why are we studying this? But let me show you a quick example that there are different kinds of equilibrium positions. And please pay attention to this. The concepts build on each other. If we have let's say we have an object here, an object here, and an object there. This is position A, this is position B, and this is position C. Please pay attention. This is a hill, a valley, and a flatland. What is common in a hill, a valley, and a flatland is that these are all, how do we call these points in calculus? Extreme points, or called the points of what? Not the point of inflation.
Minimum, maximum?
This is a maximum, this is a minimum turning point, right? Now, what is common here, listen, please. What is common at point A, point B, and at point C is that du dr is 0, which implies that F of r is 0. This is the net force on the system. And if the net force is 0, it means that the acceleration is 0. In other words, the system is in equilibrium. But look at this. Jeremy, please just focus in class and let the pig be. These concepts are really important, and I really want you guys to get this. We have agreed, please. Do we all agree that at A, B, and C, the potential energy gradient is 0? But what do you realize? If you push this ball at A, it will fall and will never return, right? But if you push this ball at B, it climbs up and then comes back to B, isn't it? If you push this ball at C, it will just roll off and you will not return, isn't it? Even though the potential energy function is gradient here are all 0, these points are different. This is an equilibrium position, this is an equilibrium position, but this is an equilibrium position, but their natures are what? Different. This position is what? Unstable, because if you push this guy, the ball will never come back to that position. It will roll off the hill. This position is what? Stable. If you push him a little bit, what happens? It will oscillate back and forth and it will land back there after some time. But this position is neither stable nor unstable, so it's what? Neutral. But in the language of calculus, how can we distinguish between this, this, and this? So this position is known as unstable equilibrium. This is stable equilibrium, and this is what? Neutral equilibrium. So at point A, you have two facts. One, du dr is equal to 0, and du squared dr squared should be what? Less than 0. That is how you determine the maximum turning point in calculus, right? Similarly, at point B, du dr is 0, and du squared, d2u and dr squared should be what? Greater than 0. This is how you determine the minimum what? Turning point. And at the neutral point, du dr is 0, and d2u dr squared will be what? Equal to what? 0. So this is how you distinguish between an unstable equilibrium, which is at the maximum turning point, a stable equilibrium, which is at what? The minimum turning point, and what? And a neutral equilibrium, which is more like at the point of what? Inflation.
Good morning, faculty and student body. At this time, please read the daily announcements. Teachers, please check dress code. Thank you. Good.
All right, please. 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 Thank you. Thank you. Let's revisit what we covered last class, because it's going to affect, we're going to move on into something when, if you do quantum mechanics, this will help you to understand quantum mechanics a lot. In our last class, we did prove or derive the law of conservation of mechanical energy. I'm not going to go back there. I'm just going to state it. You need to know how to prove it. So according to the law of conservation of mechanical energy, we know that the total mechanical energy of a system is what? Constant. And we know that E total is equal to what? U plus KE, which implies that UI plus KEI is equal to U final plus KE final. This is the basic statement of the law of conservation of what? Mechanical energy. Now, your textbook has beautifully derived this law and discussed all the intricacies on it and in plain language. So I recommend that you read those. Now, one thing that you need to understand is how to apply this particular law. Now, this is, please look up. This is the situation where there are no frictional forces in a system. Then you will apply this law. But what if there are frictional forces in the system? How would you exactly apply the law of conservation of energy? It becomes a little different. And I'm going to illustrate this with the use of an example. Alex, please. I'm going to illustrate this with the use of examples. Let us consider, look up, we've done this problem before. Let us consider a box initially given a speed v0 at the bottom of an incline, theta, and let's assume that the path is frictionless. Let us calculate the maximum height that this box will attain. Now, I can do this using Newton's laws, and as well I can do this using the law of conservation of what? Energy, and you will see the difference. Let's start first by using method 1. Method 1, we can decide to use Newton's laws of motion. Let's assume that at maximum height, it's here. This is the maximum height, h max. And that's what we want to calculate. We know that the law of conservation of mechanical energy implies that half m v0 squared plus mg h0 will be equal to half m v final squared plus mg h max. At maximum height, the velocity is what? 0. Initially, give me a second. Initially, when the box is on the surface, the potential energy here is what? 0. This would therefore imply that half m v0 squared is equal to what? mgh max. The m's cancel, and h max will be equal to v0 squared over what? 2g. As simple as a two-step process. This would have taken you at least 6 to 7 steps using Newton's second law. Please, thank you for your time, and I look forward to the next period. You have a wonderful day.
I was wondering,
Yes, please.
Mr. Chairman, here's the homework. Are you going to collect your notebooks tomorrow for review?
Yeah, I'll collect the notebooks. Please bring me your homework.